Welcome to the Opgal OGI Academy. This is our second lesson about OGI sensitivity. My name is Dr. Ram Hashmonai, Principal Innovation Scientist here in Opgal, responsible for the research and development programs related to OGI technology. Our topic of the second lesson of this lesson will be OGI sensitivity, and we will focus primarily on the environmental variables that are affecting the camera's, the technology sensitivity. So many people in thermal imaging will define sensitivity of thermal imager as noise equivalent temperature difference. This is called NETD. And when we're talking about OGI sensitivity, we want to know how the camera is sensitive to detecting gas leaks. So it's the quality of the image is not so important. It's more important how the filter of the camera, the bandpass filter that we install for the target gas, is optimized around the absorption coefficient curve of the gas in order to maximize the sensitivity. So in OGI, we either define sensitivity as a concentration path length product, which is in units of ppm meters, which is we call it the CL in the OGI equation, in the transmission through the gas plume that we mentioned in the previous lesson, or we do mass flow detection limit, which could be in any units of mass per unit time, which is we typically define this as gram per hour. In order to understand, we cannot check and actually do experiments to all hundreds of gases that OGI technology can detect. We cannot release all of these gases. Some of them are toxic. So we will do control releases, define the sensitivity of an OGI camera for a limited number of compounds, and then extrapolate for the other gases, and I will explain how we do this extrapolation. What we have is information on the absorption coefficient of any gas in the infrared thermal imaging, either it's in the mid-wave IR or in the long-wave IR. This graph is an example of three compounds. We have methane, and butane and octane absorption coefficient curve that were sampled on a 1 atmosphere standard condition, 25 centigrade, and this is and the concentration of these curves are per ppm. You can see here over here it's ppm to -1, meter to -1. So that means it's over a path length of 1 meter, 1 ppm cell, and these are the detected in an FTIR reference spectra or absorption coefficient of these three gases. And we look at the MWIR camera, typical standard filter that can detect all of these VOCs, volatile organic compounds, and we can see that they sit in different places. The methane, for example, is sitting in the middle of the filter, where the butane and octane, or actually it's butane is the yellow one and the orange one is the octane, sitting on the long wave side of that filter. Some of this absorption is not captured by the filter. So what I would like to show you that the response we can calculate actually by integrating the absorption coefficient and multiplied by the transmission, we can calculate the response, the absolute response, or specific response of each of these compounds on that filter. But if we want to do, for example, a controlled release for methane, and we determine what is the detection limit, the mass flow detection limit in grams per hour for methane, we can then do the extrapolation to the other gases by calculating the response factor. And we use the response factor only to calculate what will be the sensitivity of specific gases on any of our OGI technology cameras. We are not using this response factor as part of the quantification, because a response factor is also a function of concentration, and when we can do it only when we are very close to detection limit, we can use the calculation, the approximated response factor calculation, that take into account only the absorption coefficient, and assuming that it's not affected by the concentration. So, in many third-party studies that we have performed with our partners, or not partners, people who are we acquired their services to do our third-party test, we have established that the IC-Gas2 mid-wave IR camera, cooled IR camera, can see methane at 2 meters distance from the leak, and with the temperature difference between the background and the gas and the air, 2 degrees, 2 centigrade, we can see 0.35 grams per hour of methane in this type of conditions. So now we can do the calculation and find out what would be in this range, in this temperature difference, the MFDL, the mass flow detection limit of any other gas that we have the absorption coefficient information about it. So we have calculated all of this. We can see that for methane, this is the 0.35 for methane, and it's been done several times. It's been done in France and has been done in Israel. This number always come back to 0.35 gram per hour for methane, or 0.34 gram. This small amount of gas leak we can see of methane, we can see in this ambient condition, only 2 degrees temperature difference. So we can calculate the response factor of any of these gases using the absorption coefficient curves and the filter information, and we can see what is the response factor, and then by taking the ratio of the molecular weight, we can between the target gas and methane, we can actually convert the response factor into, and using the ground truth 0.35 MFDL for methane, converted to mass flow detection limit of any target compounds. And this table is a summary of our sensitivity in these conditions for any of these compounds. And these are the main compounds: hydrocarbon, volatile organic compounds. We have the aromatics, benzene. We have the xylenes, the toluene, the BTEX compounds, and we have a series of alkanes, and we have the methane. So these are the typical gases that we will encounter in any leak detection survey that we do in a petrochemical industry. So if we talk about sensitivity, in the LWIR camera, in the uncooled camera, in the long wave, we will do a similar process and try to calculate. We will detect it for several gases and do the extrapolation for other gases in a similar way, considering that typically methane we will see between 10 times to 30 times lower sensitivity. That means higher mass flow detection limit. For some of our uncooled long wave detection limits for cameras, I'm doing this again. For our uncooled cameras, we are talking about 3 to 10 gram per hour in this type of conditions, mass flow detection limit for the uncooled long wave cameras. So if we look at the model, the radiative transfer model that we have developed or derived in the previous lesson, we can see that in the definition, in the table in the previous slide, we defined the mass flow detection limits in temperature difference of 2 degrees and in indoors setup, which is with wind speed of 0, and also we define the range to be 2 meters. This definition implies that these are variables that are affecting the sensitivity. For example, we can see from the OGI equation down here that we derived in the previous lesson, if the temperature difference is larger between the background and the target gas plume, we can see that the contrast will be larger. So if the contrast is larger, that means that we can, that's affecting the temperature difference, affecting the sensitivity. Also, we can see here when tau, the transmission of the foreground air, is becoming less than 1, significantly less than 1, it's also decreased the sensitivity. So range actually decrease our sensitivity. And we know that wind speed, when we have high wind speed, it's also affecting sensitivity. So if we look at the model that we have derived in the previous lesson, we can see here that range, delta T, temperature difference, and wind speed are the 3 environmental variables that are affecting sensitivity, and I will discuss in the next slides these 3 variables. So let's talk about range. Range is actually affecting the sensitivity. As range gets larger, we are getting away. We have the radiance, the spectral radiance that going from the gas plume into the camera needs to go through the atmosphere, the foreground air in the medium. So in the middle, the foreground air in the middle. So tau of A, as we saw from Beer's law, is the absorption extinction coefficient in this spectral range times the concentration times the path length. The path length here is the distance to the leak. It could be 10 meters, it could be 300 meters, it could be 3 kilometers. But the longer it goes, our sensitivity goes down, and it's affecting the contrast. How does it affect? If we have extinction coefficient, which is the attenuation of the radiance with distance because of particulate matter or because of interferent gases, water vapor, it could be CO2, it could be methane, that we have a constant value of methane in the air. So the longer we go, it will reduce this number. Here, the transmission through the foreground air, and it will reduce the contrast. Reducing the contrast means the sensitivity goes down because of range. So we can see here on this graph, this is a third-party study test that we've done in France in 2015, and we have tested the IC-GAS2 camera at three distances, and in different wind speeds. And what you can see, this is for methane, and temperature difference is defined as 2 degrees over here, and we have 3 meters and 12 meters and 1 meter distance of defining what is the MFDL, which is the mass flow detection limit. And what you can see here, these two blue dots over here, this is when we have indoor setup, 0 wind speed. And we can see that this is exactly at the 0.35, these two numbers are exactly at the 0.35 gram per hour numbers as we got in previous studies, third-party studies. But as we go to 12 meters, it's always also going almost to 5 gram per hour over here. So 12 meter make a big difference, and it's probably just because we have more absorption by interference, water vapor, particulate matter, and actually methane itself, because we have 2 ppm meters. We have 2 ppm, around 1.7 ppm in the atmosphere, constant in the atmosphere. This is a greenhouse gas that is always present in the atmosphere. And if we go a longer way, the product of 2 ppm times several hundred meters can become significant in attenuating and decreasing the transmission through this foreground air layer. So then we tested this, so you can see as a function of range, and this curve, it doesn't matter in which wind speed, behave similarly because of this transmission of the foreground air. So as we go further, we need to design the cameras to have minimal absorption by interferent particulate matter and water vapor, and maximize the absorption by the target plume gas. Temperature difference is affecting the middle term here in the OGI equation. These are the Planck function radiance, integrated radiances, which is, if we take it between here, it could be the area between here and here. This is L of, let's say, the background, T of B, and here we have, so this is this area, and we can see, and the gas could be at 25 degrees. So this is, how should I do it? This is the area up to here. So what we have, maybe I could change the color. It will be even better. Let's do it in red so we can see it better. So this is the area up to 25 degrees. So this is the difference between two areas of radiance that affecting the sensitivity. So if the temperature difference is higher, we will get a greater contrast here. And greater contrast means greater sensitivity. So we have better sensitivity at greater temperature difference. between the background. And it doesn't matter if the background is colder or hotter. When the background is colder, we actually have an emission process by the gas plume. We have more emission than absorption by the gas plume, and we have a positive impact on the contrast. So what I can say over here is the delta T between the background and the gas will determine the sensitivity, and the greater this difference is, the greater the areas difference over here, and we get a greater contrast. So we have better sensitivity. And we can see that wind speed actually affecting the third part. It's actually affecting this number, the tau of G, which is larger wind speed will dilute faster the concentration, make the plume even smaller in size. It will be thinner, it will not. And what will happen is that tau will be actually closer to 1, and 1 minus tau will be closer to 0. And then the contrast will be affected by it and will become. What I want to mention, if we have no concentration, everything here, we have no gas, the contrast becomes 0. The radiance of no gas and radiance of gas will become 0. Also, if we don't have temperature difference, if temperature difference approaching to 0, we also will get 0 contrast. So the greater the temperature difference and the greater concentration, we will see the effect on the contrast and on sensitivity. So the wind speed environmental factor will reduce the transmission, actually will increase the transmission, reduce the absorption, but increase the transmission, and then 1 minus the transmission will decrease the absorption and therefore will decrease the sensitivity. To summarize this lesson, I would like to emphasize that OGI camera can be very sensitive. We have defined in several tests, third-party tests, that we can see methane with a minimal temperature difference of 2 degrees from a distance of 2 meters. We can detect and visualize plumes at 0.35 grams per hour. This is a very small amount, and if the temperature difference is larger, we can even see it in greater sensitivity. It can go to 0.1 or even less gram per hour for methane at this distance. So, and the other thing that I would like to mention is we define sensitivity as mass flow detection limit, because this is the way that we can do control release in a known leak rate and see at what temperature difference and at what distance we can see several of these gases. And then we can use theoretical information on absorption coefficient on any gas and extrapolate this, knowing also the transmission of the bandpass filter of the camera. And I would like, again, looking at this OGI camera specific OGI equation, every time we define a mass flow detection limit in mass per unit time, we have to state what is the temperature difference and what is the settings, if it's indoors, outdoors, what was the wind speed, and what is the range, what is the distance to the leak from the camera. So these are the three environmental variables that are affecting range, and it's affecting the transmission over the foreground air. the temperature difference, which is affecting the integration of the spectral radiance in the filter spectral range. So the greater the temperature difference, we showed the greater sensitivity, and the wind speed that affecting the dilution of the plume, and larger the wind speed, reduce the concentration product, integrated concentration product, path-length concentration product, and that when this becomes smaller, the contrast also becomes smaller, therefore sensitivity is smaller. Now that I summarized this lesson, I would like to remind you that we are welcoming any question. You can contact us at info@opgal.com, and we would like also to tell you that we have a document, a monograph that describing this lesson in greater details, and we have an infographic that we can share with you if you contact us. Thank you, and see you in the next lesson.